In this quick video, we're going to be reviewing how matrices can be represented as transformations, because a matrix and a transformation is effectively the same thing. Now, the standard matrix, 1, 0, 0, 1, or the identity matrix, if you think about the column vectors, so let's take this vector, 1, 0, as A, that's the horizontal vector A, 1, 0, and the vertical vector here would be B at 0, 1. B. When you're looking at transformations, it always comes down to this base matrix, and you see how the matrix and the vectors change, and then that allows you to find the new matrix. So let's take a rotation clockwise. So if I rotate this clockwise through 90 degrees, the new vector A goes down here, and B comes along here. We call it A dashed and B dashed. That's a 90-degree rotation clockwise. What is the new base vectors? Well, A dashed would be 0, minus 1. Don't forget, the 0, the top number is going horizontally. The minus 1 is going up, down. And B would be 1, 0. So before we had A, then B. So let's write that again for my new matrix. A dashed, B dashed. A dashed is 0, minus 1. B dashed is 1, 0. That means that this matrix here, 0, minus 1, 1, 0, represents a 90-degree clockwise rotation. Let's take, let's say the question is asking us to find a matrix that represents a reflection in the y-axis. Well, again, let's start with the base vector. So let's start with A being at 1, 0, and B being at 0, 1. That gives us the standard matrix 1, 0, 0, 1. Now, if I reflect in the y-axis, what's happening is I'm reflecting in this line here. And so what happens is A would move across, B would stay the same. So my new matrix, or my new vectors, sorry, A dashed is there, B dashed is there. A dashed is the vector minus 1, 0. B dashed is the vector 0, 1. And therefore that means that my new matrix is minus 1, 0, 0, 1. That's A dashed and B dashed. That represents a reflection in the y-axis. A reflection in the x-axis is exactly the same. It's just going the other way around. So a reflection in the x-axis would be 1, 0, 0, minus 1. Let's take a stretch. So let's say that I'm going to enlarge both x and y by scale factor 4. So we have our vectors, 1, 0, 0, 1. And it's being stretched by scale factor 4. So it's now 4 times as long. That means this is now 4, 0. Oh, no, sorry, wrong way around. 0, 4, and 4, 0. So for an enlargement, scale factor 4, the matrix will be 4, 0, 0, 4. You also need to know about stretches. And a stretch is a stretch in one direction, and the other direction is invariant, which means that it doesn't change. Let's take a stretch in the y-axis, scale factor minus 2, and the x-axis is going to be invariant. Invariant means it doesn't change. So if we're stretching scale factor minus 2, my x doesn't change, but my y does, and it goes down twice as long. So my stretch scale factor minus 2 in the y direction, x doesn't change, would be that. Don't forget, it's always just going back to that base matrix, and we're just saying, well, how's it going to change? Let's take a different example. Let's say that we are going to be doing a rotation by angle theta, and we're going to go anti-clockwise. Now, it's a nasty matrix to do with trigonometry, and again, it comes down to the base matrix. So the base matrix is 1, 0, 0, 1. And what I'm going to do is I'm going to rotate both of them clockwise. So that's A and that's B, sorry, counterclockwise by angle theta. So let's say that there is theta, and that there is also theta. So that's my new A, that's my new B. Don't forget the lengths are still 1. Now if I think about this length here, I can make a right triangle. And from that, if we think about the height and the width at a right triangle, that means that the width is going to be cos theta, and the height is going to be sine theta, because sine is the opposite, cos is the adjacent. Don't forget, if cos is adjacent over hypotenuse, and the hypotenuse is 1, that means that cos is the adjacent. Exactly the same logic here would mean that the height is cos theta, and the width is sine theta, but it's going to the left, which would mean that this is going to be a negative value. So my A dashed is how the A has changed. The x coordinate has become cos theta. The y coordinate has become sine theta. That's A dashed there. My B dashed is going to be the new x coordinate, which is minus sine theta. Again, don't forget, it's gone to the left, which means it's negative. The height is cos, and so it is now cos theta. That's the matrix. Whatever the angle is in degrees or in radians, we put that in. It will tell you the new matrix. You also need to know about reflections in diagonal lines. So let's take an example. Let's say I wanted to reflect a point in the line y equals root 3x. Now, for various reasons you don't need to know for the course, the matrix is given by cos 2 alpha, sine 2 alpha, sine 2 alpha, minus cos 2 alpha. And that is where the line is y equals tan alpha times by x. So you can see it's quite similar to my question here. Tan alpha is just the gradient. So in my question, if I find alpha, so I say tan alpha equals root 3. Alpha is tan inverse pi by 3. Sorry, tan inverse root 3, which is pi by 3. That's the angle. And if I then put that into the matrix, cos 2 alpha, sine 2 alpha, sine 2 alpha, minus cos 2 alpha, that will therefore tell me the matrix itself. So if I put that in, so I get cos, make sure you're putting in cos 2 pi by 3, because we're doing 2 times the answer. So if I put that into my calculator, I get minus a half. For the first one, I get minus 1/2. If I do, the next one would be minus cos 2 pi by 3. So that's obviously plus 1/2. If I do sine 2 pi by 3, I get root 3 by 2. And I do sine 2 pi by 3, I get root 3 by 2. This is the matrix that therefore represents that transformation. So what's the point of all this? Well, the matrix represents the transformation, and it means that if I multiply a matrix by a point, it will tell me where that new point goes. So we'll take, let's take our reflection. So our reflection in the y-axis was given by minus 1, 0, 0, 1. It was this matrix here. Let's say that I have a point, it doesn't matter what the point is, 5, 4, and I reflect it in the y-axis. So that's the reflection like this. If I multiply these together, the correct way around, which means I do the matrix first, acting on the point, I get the coordinate of the new point after it's been reflected. So it will be minus 5, 4. And logically this makes sense, right? Because if I'm at 5, 4, which is here, and I reflect it in this line, I should be over here, which again is minus 5, 4. And that's what we got when we multiplied the matrix together. So if I multiply the matrix by a point, it will tell me the image point itself. How might you see this in an exam question? Well, another typical example, other than just stating what the matrix might be, would be to say 2, 1 goes to 1, 4, and 1 minus 3 goes to 4, 9. It'll ask you to find the matrix that does this. So find the matrix that sends the points 2, 1 and 1 minus 3, 2, 1, 4, and 4, 9. Well, what I can do is I'll take my matrix, so A, B, C, D. I don't know what the matrix is, and I'm going to apply it to 2, 1, and that will give me the matrix, the vector 1, 4. If I apply it to A, B, C, D on 1, minus 3, that will give me the coordinate 4, 9. Each one of these is going to give you a simultaneous equation that you can then go and solve. So let's take the first one. Let's multiply it out. I get 2a plus b equals 1. And I'll get 2c plus d equals 4. From the one below, if I multiply it out, I'll get a minus 3b equals 4. And I'll get c minus 3d equals 9. I can then put that in my numworks calculator or in any other graphic display calculator. I can graph it, and I can solve to find the matrix A, B, C, and D. Solving them, I get A equals 1, B equals minus 1, C equals 3, D equals minus 2, and therefore the matrix that does send these points to the new points will be 1, minus 1, 3, and minus 2.